How's it going? So we have an exam tomorrow on acids and bases, and I just wanted to review some of these concepts. Now, it's a pretty complicated subject, even though it just seems pretty simple. Acids and bases, right? This can be kind of intense. But let's get this started. So let's just consider this list of strong acids and strong bases. And I mean, obviously, we kind of have to know like what do acids and bases do? Uh, if we look over here. Acids tend to donate these H pluses. So they have these H pluses and they just hand them out. So, they just hand out these H pluses. And the bases, well, they kind of take those H pluses back. Um, and so they kind of do this thing where they exchange these H's. And so let's consider these strong acids, this strong acid list right here. You might recognize some of these things like hydrochloric acid and some of these other ones. Um, Basically, what we can do is we can calculate the pH of this stuff by taking the negative log of the concentration of the strong acid. That'll give us a pH. And we can also take the pOH of maybe the base, and then we could take 14 minus the pOH and we'll find the pH. Because usually we don't care about pOH, usually we just care about pH. But we could sort of figure out, using this strong approximation, and keeping in mind that usually these strong acids dissociate completely in a liquid, so they have to go by these two equations that we have here. We get the acid equation here and the base equation here. Both of them are happening around the same time, but notice how the strong acids really push this equation to the right, which is we have to focus on the acid equation here. So it's just kind of this equation is just dominating over this equation. And so that's why we call them strong. Now, if we're looking at bases, of course, it's this equation that's dominating over this equation. And so we kind of push the equation to the right of this here. So basically, strong bases, as you can see, they want to pull those H pluses. So you can consider this water as a base, is this an acid or a base? I think the base is right here. So this is the base. And we have this water thing that is sitting around, and this base is grabbing H's from the water, right? And so that's how you can get this HA, because otherwise, uh, here on the left we have A, and we're just going HA, right? And then we're left with this OH on the side. So we have a really strong base here because it's just yanking H's away from water. Now, it usually does this one step at a time, right? So these bases are pulling one H from the H2O one step at a time, right? And so these strong bases feed on H pluses. And of course, the acids donate those H pluses. You look over here, we have our acid, and it's just sitting in the water. And it goes ahead and just donates that H plus over. And so it's just H3O. Okay. We usually just call that H plus, but we're looking at this H3O, H plus situation here. It's the same thing, okay? Because we don't really care about the H2O part. We just care about the H. And then we have the base sitting around, but we have all these H pluses there. And so that gives us this huge amount of pH. So that's why the strong acids give out all these H pluses, which lowers the pH. Okay, this is the lowest pH right here, and this is a little bit higher pH because this is the strong acid list. It's a little bit backwards. Okay, so just kind of keep that in mind that as the strength of the acid increases, the pH decreases, and the concentration of H plus actually increases. So it's kind of like this weird back and forth thing. But anyway, Um, so this is the strong approximation. These things that sort of split apart freely, and you can calculate the pH or the pOH just kind of using this approximation. Negative log of the concentration. Of course, for these ones over here, you have to take 2 times the concentration because they have two OHs. All right, um, and so that's a strong approximation. Now, usually we kind of mix things around, right? So let's consider titration, I guess, a little bit. Titration stuff. Because You want to be like mixing strong acids and strong bases together, or you could be mixing weak acids and bases in there. But let's just consider this, and like I said, this is a little bit complicated, so let's take this one step at a time. Let's focus on what happens at equivalence if we're titrating these two things, right? The strong acid and the strong base, uh, or a weak acid or a weak base, whatever, it doesn't matter. We're just going to titrate two liquids together, and we're going to call them um, two equivalents. And what does that mean, titrating two equivalents? It means that we've reached this point right here, where the moles of OH equals the moles of HA. Okay, and so since we're focusing right now just on strongs, we're going to kind of use the strong approximation because we're left with just strong after a strong base after a full titration. And we kind of have these equations down here that we can use. We can simplify this stuff down really, really simply to H plus OH goes to H2O for the acid part, or no, for the these equations are just simplifying these strong base titrant or strong acid as the titrant. And then we can approximate the pHs at the end or the pOH. Um, Usually we use the strong base as a titrate, like NaOH or something. So that's your titrant. So we can usually use this stuff right here. And then we'll find that the concentration of OHs at the end is kind of the moles of the base that's left over at equivalence divided by the total volume. So we kind of have to use an ice table to sort of figure out how many base ions are left over here at equivalence. Um, so let's say we're now at equivalence, which means that this equation has essentially gone to completion here. Um, and so we have this acid plus the base that combine together, and we get this salt at the end. All right, we're still just kind of focusing on two strong things really together. We'll take a look at the weak a little bit later. But when we're both strong, we can see we get something like NaCl come out. The Na came from NaOH, which is a strong base, back from the list of strongs over here, NaOH. And then we have HCl is basically the strong acid over here, HCl. So those two combine, and we get this situation where H plus equals OH at the end, and so we get a pH of 7. So we get a neutral salt if we titrate the acid and the base, both from strong, to equivalence. And it's just completely equivalence again is over here, where the HA equals 0 because the full acid has been completely neutralized, and we're left with just the A plus, or so the A minus, and some more. Here's some titration curves that will show us this in visually. See, we start out, we titrate it, we get straight to this equivalence point, and we're at a 7. This is when we have both strong acid and the strong base. This should be colored blue right here. This is the strong acid with the strong base, fully titrated, reaches the pH of 7 here. But as you can see, if we start mixing silica with a strong acid, and mix it with a weak base, well, which one's stronger, the acid or the base? Well, the acid is stronger in this case, so if we fully titrate that, we're going to have a pH of less than 7. A little bit acidic because we have a strong acid. Vice versa, if we have a really strong base and we titrate that to equivalence, we're going to end up slightly over 7 because it's a strong base, because the base is stronger. This is kind of a logical thinking process. If we look at the weak, like both a weak acid and a weak base, then we don't really know. Let's go back to this list. That was a visual of this list right here. Again, we're at equivalence, We've titrated both of them to equivalent, completely neutralize the acid here. This equation has fully gone to completion. And then now we're just kind of looking at the combination of whether we have weak acids and weak bases. Weak acids and weak bases are just the ones that are not in that list. Let's go back to this list over here. It's not one of these 7 on the left or 8 on the right, then it's weak. And because it's weak, we have to do this situation here where instead of having a full H plus and we can use the little pH negative log of concentration, we can't really do that. We have to realize that the H plus is going to be like a really, really small amount of the initial concentration. So we have to use this little partial ionization. Both both sides of this equations are happening at the exact same time, right? The weak acid dissociation and the conjugate base hydrolysis. Both those equations, oh my god, what happened? Both equations are happening at the same time, and we're doing weak acids and bases. We have to realize that we have to use this kind of approximation. We can find the H plus concentration by taking the concentration of the weak acid times its Ka value. We'll talk about Ka values a little later, but let's just realize we have a Ka value. And then we can square root that. And that'll give us the H plus concentration of a weak acid at equilibrium, just by itself. If we have the OH, we could do the same thing, just using the Kb. And this is just a weak acid approximation. We're just kind of looking at it in isolation by itself. Say we've titrated, we fully titrated, say, a strong base and a weak acid, and there's some leftover weak acid, uh, then I believe what that means, so if we have leftover weak acid, and we couldn't fully titrate the base, I believe that we have to use the weak approximation, but it's kind of hard. We have to figure out when do we use the weak approximation and when do we don't. Let me look back over here. Strong or weak approximation. I think if they're both weak, I mean, you think about it, like what's left over here at equivalence? Um, is the base a weak base? If it's a weak base, you have to use the weak approximation. If it's a strong base left over, then you have to use the strong approximation. And it only makes sense. It's just hard to verbalize this, I guess. Some difficult stuff. Um, so again, let's just kind of consider it. If we have a strong base and a weak acid, obviously we're going to get a more basic solution because the base is stronger. We also get this thing where HA is approximately equal to the concentration of OH. And so we get a little bit greater pH of 7. If we have the strong acid mixed with the weak base, we can clearly get a more acidic situation here. But again, this is kind of more at equivalence. We can use this little chart. But now let's consider the facts where points where we're not at equivalence, like maybe we're at half equivalence. Half equivalence is a really good point. So equivalence was this point, but half equivalence is kind of more like around here. Half equivalence is a good point because we can use this stuff, where we get the mole of OH is half the mole of HA. Or we did a half titration. So we could set HA equals A minus, because we have about half acid and half base. And then we can set pH equals to pKa of the HA. And so the half equivalence point is a really nice point. If we're not quite like at the half point, then we would have to use the Henderson-Hasselbalch. Also, if we're past, just slightly past this point, this is kind of like the buffer region. The buffer region is this region that you can see over here in gray. Uh, this buffer region, we have to use the Henderson-Hasselbalch if we're using weak, um, if we're mixing a weak in there. One of the weak acids or bases, we have to kind of do this. So remember, if we're kind of both strong situations, and we could just kind of use the strong approximation. All this stuff happens only if we have a weak involved. So yeah, so again, it gets really complicated and convoluted here. If we go past equivalence, then it pretty much doesn't matter. We always use the strong OH molarity, because we always just have OHs left over, pure OHs, and we just I think this is when we have to figure out whether we titrated with a strong or weak base, and then here we would use either the strong or weak approximation. It's quite possible. See, it's always really complicated to figure out when we use the strong or the weak approximations. But this is the strong. Again, you take the OH equals the moles of A at Q divided with the volume. And then for the weak approximation, it was this stuff over here. Just H equals the concentration times Ka. But I think the Henderson-Hasselbalch equation might be a little bit more important. This one right here. We can set the pH of the buffer. Uh, if we're not quite at equivalence, we're going to have a little bit of each, and so we have to sort of figure out how that's going to change the pH. And so, yeah, so if we're not at equivalence, we have to kind of use the Henderson-Hasselbalch equation, especially for weak acid in there. What is this buffer stuff? Buffer is just a mix of the A minus and the HA combined together, and you try to get them to an equal ratio such that pH equals negative log of Ka, and this goes away. So that's kind of the ideal buffer right there. Um, if you go ahead and add the H plus into the buffer, it's going to react with the A minus and make some of this HA. The opposite happens to the OH. Usually we have to use a little bit of nice table to set this up. And this is a little bit overwhelming. So it's hard to keep track of everything. But we've basically talked about most of the stuff we need to know. It's hard to keep track of it. Let's discuss the K's, I guess, real quick. So we have this Ka and Kb. This is the acid strength essentially versus the base strength, and we have to basically take that equation that we had over here, and we set HA on the bottom here, these ones on the top over here. That gives us the strength of the acid. It's a little formula right here we can kind of use. Usually this X can be ignored because it's so small if this is weak. Notice how we usually take the H, well, we have to take the HF, like the HA and then the A minus, like its conjugate base. And we have the strength of water right here is 10 to the negative 14. Okay, these K's are only temperature dependent, so it's the only way you can change the K values is by changing the temperature. The Kb is found by taking the A on the bottom here, the HA and the OH on the top there. We could do interesting things with these K values because if you're dividing two equations together, then you divide the two K values. But dividing the two equations is the same thing as adding the reverse of the second one. And if you add two equations, then you multiply the two K values. Okay, and usually we do this. Usually we do this when we have some steps to take, like right here. Like maybe we're dissolving something, so we think about the KSB, and then we're trying to form something, so we think about the KF, and then we get the net equation, and this K is equal to the multiplication of the S of SP times the F values. So this is how the KSP and the KF are related. If we're trying to dissolve a salt, use this equation. So the solubility, molar solubility, so we take the Ks is equal to m times the power of p, x times the power of q, and this is concentrations. We also have the ps to the power of p, or the qs times the power of q, so that ps is equal to m concentration, and qs is equal to the x concentration. These are the same things. Now we sometimes need to calculate q to see what's going to be happening with the q versus the k values, and you kind of know q versus k values. It depends whether the q is greater than the KSP or less than the KSP, whether we precipitate or not. Okay. Here's another way that we can combine multiple KSPs. Like say we have a high KSP, and that gives us this critical OH that's required to be able to make this precipitate. But we want to figure out, how much is left over of the first um, ion, and so we have to take the the OH concentration that we found here, and then we put it in here. Actually, if we have a n squared, it wouldn't make sense to keep it on the left side. Well, whatever. Point is, you want to like square root this if you have a square there. That's the point. So yeah, so we kind of have those Ka values, Kb values, Ksp. There's even a K value, precipitation value. Some more K values right here. What is this trying to say? So this is stronger base. I can't remember. Maybe we should look at the Ka values. I think that was over here. K3 seems to be the strongest. Okay. No, this is the strongest. Oh, we have more concentration of H pluses, less concentration of over that. Yeah, color coding is not always obvious, but the idea here is that we have more concentration of this one and less concentration of that one. So that kind of doesn't make a lot of sense. But stronger K values, KB values, will obviously donate more OHs and less OHs over here. And same thing right here. This is most, and this is the least. And that's why when we start to consider multiple acids, steps donating multiple H's, we usually just focus on the first. So you can see we like carry the Ka, the third. We approximate it as just saying, probably just the H pluses just from this first situation, because this didn't donate very much H pluses and this didn't donate very much H pluses at all. So we kind of like knock those away and just focus on that. So that's if we see H plus is being donated in multiple steps. What else could we kind of discuss here? Because it's probably getting a little bit long. This KF maybe, this last thing right here. Um, not too sure why this is. Okay, but anyway, so what could we do? What could we do? Adding H plus acids to the salt mixture is gonna react with the A minus, so it consumes the salt. Adding OH is also consumes the salt. I guess adding anything increases the solubility of the salt. Um, uh, say F. So this is for formation of when we have a metal plus a ligand that are combined together, and we have to use this kind of KF. Use the ML and the concentration of that stuff, and we just no solids. Oh, this is the total. The total. Okay, so if we have K total, maybe I could put the underscore with this because I can't remember everything. And with that, this is K total. Should I just call it KT? I really do need this underscore right here because otherwise I will get confused with this K because it looks the same. So this is KTOT, K total. And the way we got that was we multiplied these two together. That, right? So this is correct, yeah, because we have the X in there as well. Here's the net equation that might happen. Salt plus the ligand. And we have the one that's formed plus the base in there. Um, right. I think we pretty much covered all this stuff. The titration curves, the two different equations that we have, the strong and weak approximations. Um, what happens when we add acids and bases to either the buffers or the this salt solutions. Um, so yeah, so this is kind of a really complicated situation. It requires sort of remembering all these rules. And here's an ionization ratio I haven't talked about, but it's okay. It's just the H plus is EQ divided by the HA initial, or the OH at EQ divided by the A initial. Relatively simple stuff. You could find it by doing the square root of K divided by the HA initial, or square root of KB divided by HA initial. Um, okay. I think this is probably where we have to wrap this up because, like I said, it just gets a little bit crazy. But we have to remember strong acids, strong bases, and how they actually pull H pluses away and sort of snatch them up or donate them. And then, depending on whether it's strong or weak, we have to look at what happens at equivalence. Or if it's not equivalence, then we might have to use the Henderson-Hasselbalch uh, equation to try to figure out what's going on, or maybe it's a half equivalent, so maybe we have to use the strong or weak approximation, depending on what is left uh, after titrating. Hopefully it was a helpful video, and thank